Yes. Okay. Hi, everyone. Today we have the lecture number 5. It is a series number 5. And you remember what happened in previous lectures. You remember that our great idea was to model risky asset. And for risky asset, we have chosen ITO processes. What is ITO processes? Maybe you remember that ITO processes or diffusion processes can be written algebraically as this form. I see this mistake, AXT multiplied dt plus BXT multiplied dz, where x it is our stochastic process. For example, it's stock prices. Okay. And now I would like to remind you what is the meaning of coefficient function in this ITO process. Yes, you see that function A from xt and B from xt. So A from xt, it is average shift. It is mathematical expectation of shift during the small time. And function B square, it is variance, so it's mean shift, but the second order, mean shift of the second order. And we know that mean shift of the high order is zero, and we assumption that it is a very small time. It is dt tend to zero. You remember some example of this diffusion process. It is Brownian bridge, and you see that A in this case, it is this ratio. Yes, it is this ratio before dt. Yes, the xt equals A dt plus B bt. And B in this case, you see, equals, Misha? In this case, function B
is equals 1.
1. Okay, well done. The second example was Einstein-Uhlenbeck process, and in this case, function A, this minus A multiplied xt in function B is, Misha, function B?
Lambda.
Sigma. Yes, just constant sigma. And this next example was geometrical Brownian motion. And in this case, you see the function A, it is product mu and xt, and B product sigma xt. And this example, this geometrical Brownian motion, can be written as the x divided by x, the x divided by x. So we just divided the both sides by xt. You see, yes? So it's the same. It's up to you. If you want, you write in this form. If you want, you can write in this form. And after that, we can task how you can solve this differential equation. So maybe it is as by integration of left and right side. But for example, in this case, if we integrate, you see that it is d ln x. But what is the derivatives from logarithm x? We don't know, because x is a stochastic process. but for this we know eta lemma. Yes, eta lemma answered on the questions how we can find derivatives from the stochastic process. And the eta lemma states that if we have a stochastic process in the form as diffusion, yes, as we repeated today already, dx equals a xt dt plus b xt dz, where z is the Brownian motion or Wiener process. We can write z, b, t, w, t. It is up to you too. Yes. And lemma eta states that if we have process in the form 1, and if we have function g, it is not random function. So for this function, derivatives equals, derivative is, you see the derivative is process eta 2. Yes, and we proved this on the previous lectures. So you see that the form the same. So we have coefficient function and multiplied dt, and other coefficient function multiplied dz. For example, function b from xt in equation 2, it is, what is this function? You see, Misha? Do you see?
Yes.
What is this?
Yeah.
Derivatives dg, да? Respect
dg
to
dx.
In multiplied constant b. So again, if we have stochastic process in the form 1, and we have function g from this process x and from time t, so derivative dg is process eta 2, and we can find these derivatives according the formula 2. Yes. Okay. And now we think what is for this diffusion we can choose for describing our risky asset, stock prices, for example. Maybe it's process Amstein-Uhlenbeck or Brownian bridge, or geometrical or arithmetical Brownian motion. And for this choose for making decision, we can remind the first lecture where was considered the next problem. If we have investment, for example, S, so the velocity for this no S, okay, no S, because this is, for example, A capital. So velocity of changing this investment for the time t, velocity, yes, dA respect to dt is proportional R, it is interest rate, and A from T. Yes, you remember this equation. And after that, we said that it is equation of the first order, and for solving, we need to divide their both sides by a and multiply it by dt, and it is dA t divided by a on the left side equals r dt. R dt. And after that, we can integrate the both side. So in this side, it is ln logarithm, natural logarithm, a from t, at, and this r rt plus ln c. Constant, no, constant c or ln c, and after that ln r minus ln c will be ln, okay, will be ln a divided by c, so a equals c or a 0 multiplied e exponent to the power rt. So yes, it is about motion on investments. Yes, it's about motion on investments, and if we have interest rate R. But if we now consider no investment but stock prices, so we know that the velocity of stock prices, dst divided by dt, is proportional. So, okay, for stock prices, ds velocity dt, velocity of change stock prices, is proportional constant no r, because r it's interest rate, yes, but for stock price it is interest rate no r, but it is no some mu st, but it's very similar, yes, this and this very similar, only different constant. But for investment, the future value depends only on time and initial value. But for stock price, it is the value of stock price depends not only only on time, but on chance too, because it is stochastic process. So we can write this as mu s dt and plus stochastic term sigma s dz, where mu and sigma is called drift and volatility. And you see that the formula 2 is called geometrical Brownian motion. Yes, geometrical Brownian motion. Okay. Is it clear? Yes?
Yes.
Okay. So, for example, how we can use this, for example, for the economical aims. If we know volatility for some stocks, of any company, if we know expected rate for example, 15%. So we can substitute this value in our geometrical Brownian motion. Yes, ds divided by s equals mu dt plus sigma ds. Mu it is 15% and sigma 30%. So we can this differential equation with concrete constants. And you know that the key rule of stochastic calculus, and this rule is that dz equals epsilon square root from dt. It's very important. So I remind you again, dz equals epsilon multiplied square root from delta t, where epsilon is random variable, and in our case is with normal distribution, and parameters of this normal distribution is 0 and 1. 0 means mean and 1 means variance. Variance, yes. And how we can apply this? Suppose that S0 equals $100, or euros, or hryvnia, I don't know. And for example, if we consider interval of time delta t equals 0.0192, it just seems that it's 1 week or 1 day. I don't remember. Maybe 1 week. One week. So the change in stock price we can compute as according to this formula. ds it is discrete variant, and in this variant we can write instead. We can write instead ds delta s, delta s divided by s. So delta s equals s, but s 100 multiplied this, we rewrite, multiplied delta t, this, plus 0.3 multiplied square root from 0.0192, and it is 0.0461, and multiplied epsilon. So according to this formula, we know that change in stocks for this interval of time, maybe it's week, equals 0.288 plus this stochastic value. So we don't know what is epsilon. Epsilon is exactly, but it is normal distribute random variable, and we can substitute some value. It can be, for example, minus 0.2 or plus 0.35. So from this we can find the interval from this change. It will be this plus minus no, this. Okay. So in this way we can apply this formula. So what is about solving this stochastic differential equation? First, we need to know what is integral dzt from t equals 0 to t capital, We can write this as integral from dz. It is formally it is z, yes, and substitute the up, and after that down value, and it will be formally zt minus z0. But this result is just a way of saying that it is a sum of normally distributed random variables. So if you see integral and this integral respect to Brownian motion Wiener process, yes, that t it is a Wiener process or Brownian motion, and we can write this up to you. So it's just a sum of epsilon t, and you know that the sum of epsilon t, it is a random variable, and this random variable has normal distribution too, and parameters mean 0 and variance t, because number of this number of terms in this sum is t. Yes, so we can write these variables as mean plus but mean is 0 plus epsilon square root from t, and its equivalence in distribution. So let's consider example 1, diffusion. This diffusion is called arithmetics Brownian motion. Arithmetics Brownian motion. It is just dx equals mu dt plus sigma dz. And we would like to solve this differential equation. So we integrate this, integrate this. Mu is constant, so we write before integral, sigma constant before this integral. This integral, it is xz minus x0. This is xt, sorry, xt minus x0. So xt, the solution of this xt equals x0 plus mu t. Why mu t? Because mu constant, but integral from dt it is t, and t from 0 to t capital, it is t capital minus 0, or only t capital, yes? And in this case, it is sigma constant, and this integral, it's epsilon square root from t. So it's solution of this equation, arithmetical Brownian motion. Okay? And the next. And now we would like to find solution of this differential equation. It is geometrical Brownian motion, you see. And first, what we do, it is we would like to write this dx divided by x as d from ln xt. And after that, we need to apply lemma eta, because our function g, in our case, it is ln xt. And our dxt equals x t mu dt plus xt sigma xt sigma dz. So it is from this, yes, dx, we multiplied the both sides by xt. So it's our stochastic process, and we would like to find dg. And for this, you remember lemma eta, yes? You need to find dg respect to dx. It's partial derivatives. So it will be, we have Maxim. What is derivatives, this function respect to dx?
Максим відпав, напевно, у нього знову щось вибігає.
Відпав вже, да? Окей, Міша.
Multiply et.
What is we have ln xt. If you would like to find derivatives from this function, g derivatives x. What is this?
I thought ln x and derivative ln, I thought it was like epsilon multiply x. I'll check. It equals 1 divide xt.
Yes, okay. Thanks. Okay, and the derivative second order. It will be, Misha, please, derivatives from this. Derivatives from this. Do you know?
Wait a second.
Okay.
Minus 1 divide x square.
Yes, okay. Okay, and now we need substitute all this, and derivatives dg to respect t is 0. Yes, because function g, it is ln xt. So partial derivatives g respect to t is 0. And now we need all this substitute in lemma eta. And do you remember? Значит, in lemma eta dg, dg equals dg equals, and in the bracket it is, do you remember, no? Okay, let us, we can remind, maybe lemma eta, this. So dg respect to dx multiplied a, this, it is 0, yes, 0, and the second order multiplied half and b square, okay? So dg respect to dx, it is 1 divided by x, it is 1 divided by x, and multiplied function before dt. This, it is a, and it is b, and it is, so multiplied a. Multiplied a, it is x and mu. So this x crossed plus derivatives respect to dt is 0, plus 1 divided by 2, multiplied the second derivatives, it is with minus, so no plus, minus, and multiplied
without square or not, because we then have a xt, but we don't have t here, so we can, ну, воно не скоротиться виходить, бо у нас тут просто x, а там x.
І multiplied b square, а b square це x square and sigma square. Sigma square and x square cross and dt. So you see, we have mu minus, like this, in this bracket, mu minus 1 divided by 2 sigma square dt, and plus, and in this bracket, what we have, we have just dg, dg respect to dx multiplied b. Dg respect 1 divided by x, 1 divided by x, multiplied b, b is x multiplied g, and dz. Yes, so we have this expression, this formula. So if you would like to find d ln xt, this g, yes, so according to lemma eta, we have this formula, and after that we would like to integrate this and this from 0 to t capital, from 0 to t capital, from 0 to t capital. Integral from d ln xt is just ln xt, yes, and after that we substitute instead t capital, it will be ln xt minus ln x0. But in your homework, for example, you need to find from, no, for example, from delta 1 to delta 2 d ln from xt. Oh, for example, yes, and it will be ln xt, for example, delta 1 or delta 2, or for example, it can be t1, t2, yes. So first ln x delta 2 minus ln x delta 1. So it doesn't matter what this value delta 1, delta 2, a, b, 0, t capital, okay? So in this case, we find integral from 0 to t capital, from 0 to t capital. Yes, and you see it is ln xt minus ln x0. In this case, it is constant, and we write it before integral. Integral respect to dt just t, and first up value it is t minus 0, it is t, and sigma integral from differential on Brownian motion, and we know that it is just this integral. If we find, it will be epsilon square root from t. Square root from t. So xt equals x0 exponent to the power, this bracket, multiply t capital plus sigma epsilon square root from t. Okay? It is solution of this geometrical Brownian motion. And after that, we can find the fair price of derivatives, But you need to know definition. What is fair price of derivatives? According to definition, fair price of derivatives is discounting mathematical, so this definition, this definition is discounting, it is this mathematical expectation of Pio function. So it is discounting mathematical expectation of Pio function. It is f. I don't know if you remember what is Pio function. Pio function, no, maybe I remind you. So, for example, if we have two scenarios, today we have $100 and there are two scenarios, 150 in the up scenario and 80 in the down scenario. And for example, we have strike price, K equals 120. So, per function, it is what money you get in up scenario and in down scenario. In up scenario, our profit will be, Misha, in up scenario, what is profit in up scenario?
It's like current price minus the price we sold and minus commission, like P.
Yes, but yes, it is net profit. But per your function, it's just this difference between between market price, current market price, and K. So per your function f equals this S, because it is no current market price, it is ST. Or SN, ST minus K, minus the strike price, and it is ST minus K with plus, and it means that in up scenario it is 150 minus 120, but in the down scenario is it just zero? Yes, just zero. You remember, da, Misha?
Yes.
Yes.
So if a current price is less, then it's zero.
Yes, okay. So fair price. For example, we can denote this as C for call option. C call equals discounted mathematical expectation from this payoff function. And after that, we write this. No, discounting. It is 1 divided by 1 plus r to the power n, or e to the power minus rt. It is the same. It is e. It is mathematical expectation of payoff function. Payoff function at the current moment. It is our model. It is our model. It is a geometrical Brownian motion. It is a solution of this equation. It is geometrical Brownian motion. It is our solution. It is our solution. It is r minus sigma square divided by 2t plus we have written epsilon sigma square root from t, but now we write instead epsilon z. So what is mathematical expectation in the continuous case? Do you remember? If we have discrete case, yes, for example, we have x1, it is value of a random variable, x2, x3, and so on, with probabilities p1, p2, and so on. What is mathematical expectation in this case? In this case, do you remember? But you need to repeat, and you have written input test. Okay.
Yes, I remember it when I write it in the test, but now I forgot.
But so it is x1 multiplied p1 plus x2 multiplied p2 and so on, xn multiplied pn. It is in discrete variant. If x is a discrete variable, but if x is a continuous variable, random variable, so mathematical expectation is integral this x this x multiplied p, x multiplied p, x multiplied p, but in continuous case, it is x multiplied probability function. And it is normal distribution. So the density of the normal distribution, e to the power minus z squared, divided by square root from 2p. And after that, we can write this as difference of two integral, this multiplied to this, minus integral k capital multiplied to this. And after that, we can write as before integral, because it's constant, e write this, you see, and we need to do some technical, not deformation, manipulation, technical manipulation, and replace this variable. And after all this, we obtained formula S multiplied phi from D1 minus e to the power minus ft k, you see k, but this integral, it is integral for normal distribution. So and after that we can compute the limits, down and up limits for this integral, and it's called Black-Scholes formula. So what is this formula? S multiplied f from d1 minus k e to the power f, yes, where it is function, it is cumulative normal distribution, and d1 and d2 we can calculate according to these formulas. And on these pictures you can see Black-Scholes. And this formula was published in 1917. And this model is often good as a first approximation. And really, this formula led to the boom in option trading, and had a huge impact on the theory of probability. This formula don't perfect, but is not a good approximation to security price, and everybody knows this, but this formula is very good as a first approximation. So now everyone uses this formula. This formula has some assumption, the assumption about riskless rate, about the model for risky asset, and about dividend. About riskless rate, it is the rate of return on the risky asset is constant and called the risk-free interest rate. And for lend and for borrow, it is the same interest rate. About model for risky asset, it is random walk. The log return of stock price is random walk with drift, so it is geometrical Brownian motion, and we will assume its drift and volatility is constant, and the stock doesn't pay a dividend. There are assumptions on the market. There is no arbitrage opportunity, so it means that no way to make a riskless profit. The second, it is possible to borrow and left any amount, even fractional, of cash at the riskless rate. The next, it's possible to buy and sell any amount, even fractional. And the next, the above transaction does not incur any fees or cost. So we have a frictionless market. And for example, how we can use this formula if we know that interest rate 5%. So we write our capital 5%, volatility 20%, sigma 0.2. The value of stock today, it is the value of stock today. This S0 or only S is 10. It is 6 months European call option or put. So 6 months, it is a time 1/2. And strike price 9. It is K9. After that, we can compute D1, D2, find this normal distribution for this and for this. We can use formula, we can use Excel, we can use Python for this. And after that, we substitute all this in formula, and you see that the fair price is 1.3498. And after that, we can compare this fair price and premium on the side. And after that, to make a decision. So maybe it's all for today. And today you have known the formula of Black-Scholes, but there are another way to derive this formula. And really, Black-Scholes used another approach, and they used approach of building riskless portfolio. And what is portfolio, what is riskless portfolio, about all this, you will know on the next lesson. So, have you any questions?
Probably no.
Okay, so stop recording.